What if I told you that, right now, somewhere in the universe, there's a place where the laws of physics break down, where time itself can freeze, and where even light, the fastest thing in existence, can never escape? Imagine a region so dense, so powerful, that it can tear apart stars, warp reality, and challenge everything we think we know about the cosmos. This is the world of black holes. Mysterious, terrifying, and utterly fascinating. If you're ready to journey to the edge of the unknown, to witness the most extreme phenomena in the universe, and to explore the secrets that could rewrite the rules of reality, you're in the right place. Don't miss out on the next mind-bending discovery. Hit that subscribe button and join us as we dive into the heart of darkness, where science meets the impossible. At this very moment, somewhere out in the cosmos, there exists a patch of space tinier than a city block, yet it contains more mass than 1 billion suns put together. In this place, nothing can escape, not light, not time, not even you. We'll journey into the realm of the smallest black holes ever discovered, witness the mightiest ones ever found, observe stars being torn apart, and dive into concepts that could upend our entire understanding of the universe. If you find this exploration fascinating, consider showing your support. Now, let's begin our descent at the very edge of the unknown. Picture compressing our entire planet into a sphere no bigger than a marble. Every mountain, every ocean, every living thing, all squeezed into something you could hold in your palm. The gravity from that marble would be so overwhelming that if you stood just a few feet away, you'd never move again. You'd be stuck there, forever. Now, imagine doing the same with a star 20 times heavier than our own sun. That's what a black hole is. But here's a common misconception: a black hole isn't a hole at all. It's not empty space. In fact, it's the opposite. A black hole is the densest object we know of. So much matter is crammed into such a tiny region that the very fabric of space and time bends around it. Space and time curve so sharply that every possible route, even the one light would take, leads only inward. This isn't just theory. It's been confirmed. We have images, we have data, and we've even detected the ripples black holes send out when they crash into each other. Let's pause and think about light. Light is the fastest thing in existence. Nothing in the universe moves faster. It travels at over 670 million miles per hour. At that speed, you could circle the Earth more than 7 times in a single second. Light is so quick that we use it to measure distances across the universe. And yet, black holes can stop it cold. Not because they grab light with some invisible force, and not because there's a wall in the way. The real reason is even stranger. Near a black hole, space itself is falling inward faster than light can move outward. Imagine trying to run up an escalator that's moving down faster than you can run up. No matter how hard you try, you'll never reach the top. You'll always be carried down. That's what happens to light near a black hole. Space is the escalator, and it's rushing toward the center faster than anything can escape. The boundary where this happens has a name: the event horizon. We'll explore that boundary soon. But first, understand this: the event horizon isn't a surface you can touch. It's not made of any material. It's simply the point of no return. Once you cross it, every direction, forward, backward, left, right, even if you try to stand still, leads only to the center. What lies at the center is something our math can't fully describe. It's a point of infinite density, infinite curvature, a place where the laws of physics as we know them break down. Scientists call this the singularity. But don't let the math fool you. Black holes are real, physical objects. They exist in our galaxy. In fact, astronomers estimate there could be as many as 100 million black holes in the Milky Way alone. Most are invisible, drifting through space, pulling on nothing, revealing themselves to no one. There could be one just a few light years away, and unless it passed near a star or a cloud of gas, we'd never know. Some black holes are small, if you can call something with the mass of several suns small. These are born from dying stars, and are scattered throughout galaxies like ours by the millions. Others are so enormous it's hard to imagine. Sitting at the centers of galaxies, these giants contain billions of times the mass of our sun. They hold entire spirals of stars in their gravitational grip. Without them, galaxies might not exist at all. And then there are the ones we haven't found yet, black holes that may have formed in the first moments after the universe began. Ancient relics, still drifting through the darkness, waiting to be discovered. Over the next 2 hours, we'll visit all of them. We'll cross the event horizon. We'll watch stars get torn apart. We'll even hear the sound of 2 black holes colliding from over 1 billion light years away. But first, we need to understand the boundary itself, the invisible line that separates our universe from the unknown. What happens at the event horizon changes everything. Imagine yourself floating in space, far from any star, drifting toward a black hole in the distance. At first, you see nothing unusual, just empty space. Maybe a faint warping of the stars behind it. Their light bends around something you can't see directly. The black hole itself is invisible. There's no surface, no edge you can see, no warning sign. But there is a boundary, and once you cross it, the universe you knew is gone forever. The event horizon isn't a physical barrier. You can't touch it. You can't feel it. If you were falling toward a large enough black hole, you might cross the event horizon without even realizing it. No alarm, no sensation, no flash of light. One moment you're in the universe, the next you're somewhere else entirely. Here's what makes this boundary so terrifying from your perspective. As you fall inward, nothing seems wrong at first. Time feels normal. Space seems normal. You might look back and still see stars, still see light from the universe you left behind. But that light is the last you'll ever receive from the outside. No signal you send will ever escape. No message, no call for help. You've crossed a one-way door that the universe has sealed shut. This is confirmed by general relativity. Einstein's equations predicted event horizons over a century ago, and in 2019, scientists captured the first direct image of one. A glowing ring of superheated gas surrounding a shadow. That shadow was the event horizon of a supermassive black hole at the center of the galaxy Messier 87, over 55 million light years away. But what actually happens if you cross that invisible threshold? What would you experience if you truly fell through the event horizon? The answer depends on the size of the black hole, and this is where things get truly bizarre. For smaller black holes, the kind that form when massive stars collapse, the event horizon sits close to the center. The gravitational pull changes dramatically over very short distances. If your feet are closer to the center than your head, they would feel a much stronger pull. This difference in gravity would stretch you violently. Scientists have a term for this process, and we'll explore it in detail soon. But for now, understand this: with a small black hole, you'd be torn apart before you even reach the event horizon. For supermassive black holes, the story is different. These cosmic giants are so large that their event horizons are much farther from the center. The change in gravity across your body would be gentle, almost unnoticeable. You could fall through the event horizon of the black hole at the center of our galaxy and feel nothing unusual for hours, maybe even longer. But don't mistake gentle for safe. You're still falling toward the center, and nothing, not the most powerful rocket, not even light, can reverse your course. The destination is inevitable. Only the journey changes. There's another effect that's worth considering. From the perspective of someone watching you fall from a safe distance, something very strange happens. They would see you slow down as you approach the event horizon. Your image would stretch and fade. Time itself, as they observe it, would seem to crawl for you. They would watch you approach the boundary forever, never quite crossing it. Your frozen image fading into darkness over billions of years. Meanwhile, from your perspective, you fall through in an instant. This isn't science fiction, this is what Einstein's equations demand. Time moves differently depending on how deep you are in a gravitational field. Near a black hole, that difference becomes extreme. And yet, the event horizon is just the beginning. Beyond it lies something even more unsettling, a place where the gentle fall becomes a violent end. Your body is about to be stretched into something unrecognizable. Let's imagine you in a spacesuit, dropped toward a black hole. Not a simulation, not a thought experiment, the real thing. What would your final moments actually feel like? The first thing you'd notice is the view. As you fall closer, the black hole doesn't look like a simple dark circle. It appears more like a lens. Light from stars behind it bends around the edges, creating a bright ring. Stars that should be hidden behind the black hole appear displaced, smeared, sometimes even duplicated. The entire sky warps into unfamiliar shapes. Constellations you've known your whole life twist into something alien. This is gravitational lensing, and it's been confirmed by observation. Einstein predicted it, and astronomers have photographed it around black holes and galaxies throughout the universe. As you continue falling, the distortion grows. The ring of bent light around the black hole becomes sharper, brighter. The darkness at the center expands in your vision. You're accelerating now, pulled by a gravity stronger than anything you've ever experienced. But here's something odd, you don't feel the acceleration. Gravity doesn't push you, it pulls everything around you equally. Your body, your suit, the air in your lungs, all of it falls together. You feel weightless, peaceful, almost like floating in calm water. But this feeling won't last. The real danger isn't the fall itself. The danger is the difference in how hard gravity pulls on different parts of your body. Your feet are closer to the black hole than your head, even if that difference is only a few feet. Near a small black hole, the gravitational pull on your feet can be dramatically stronger. This creates a stretching force. At first, the stretch is minor, a slight tension, like being gently pulled in two directions. But as you fall deeper, the difference in gravity increases. The pull on your feet intensifies while your head experiences slightly less. The tension builds, your spine elongates, your body begins to distort. This is where size matters. If you're falling into a stellar, mass black hole, one formed from a collapsed star, with maybe 10 or 20 times the mass of our Sun, the stretching becomes lethal long before you reach the event horizon. The difference in gravity across your body grows so extreme that your tissues can't hold together. You're pulled apart, not quickly, not cleanly. Atom by atom, your body elongates into a thin stream of matter spiraling toward the center. Scientists call this process spaghettification. The word sounds almost playful, but the reality is anything but. But suppose you chose a different target. The supermassive black hole at the center of our galaxy has over 4 million times the mass of our Sun. Its event horizon sits about 7 million miles from the center. At that distance, the change in gravity across a human body is tiny, less than 1% of 1%. You could cross the event horizon and feel almost nothing for a while. The problem is that once you cross, you can't stop falling, and as you continue inward, the gravitational gradient steepens. What felt gentle at the horizon becomes violent. As you approach the center, the stretching begins. The same fate awaits. You simply have more time to contemplate it. There's another factor most people forget. As you fall, time behaves strangely. From your perspective, the fall feels normal. Seconds pass like seconds. But if you could somehow look back at the universe outside, you'd see it aging rapidly. Stars moving faster, galaxies evolving, the universe racing toward its distant future while you drift toward your end. You can't send a message back. You can't warn anyone. Everything you see from inside is the last light that will ever reach you from the outside universe. And soon, even that fades. Ahead of you, there is only darkness. And at the center of that darkness waits something our physics cannot explain. But before we reach the singularity, we need to understand what happens to your body in those final moments. The stretching is about to become extreme. The word, spaghettification, might sound silly, but what it describes is one of the most violent processes in the universe. And it happens to everything that falls into a black hole, every star, every planet, every astronaut who drifts too close. Let's break down what happens as you approach the heart of a black hole. Gravity, as we know it, weakens with distance. On Earth, the ground pulls you down with a certain force. If you climb a tall mountain, that force drops ever so slightly, not enough to notice. But it's measurable. Now, imagine gravity so powerful that the difference between your head and your feet is not just a minor detail, but a force that could tear you apart. Near a black hole, this gradient becomes extreme. If your feet are just a meter closer to the center than your head, they might experience hundreds or even thousands of times more gravitational pull. Your feet accelerate faster than your head. Your body stretches. At the same time, gravity pulls from all sides toward a single point. This creates a squeezing effect perpendicular to the stretch. While you're being elongated vertically, you're also being compressed horizontally. Your body becomes thinner and thinner, while growing longer and longer. The result is a strand, a ribbon of matter that once was you, now stretched across thousands of miles, spiraling toward the center of the black hole. This isn't just theory. In 2020, astronomers actually observed a star being spaghettified in real time. The star wandered too close to a supermassive black hole about 215 million light-years from Earth. Telescopes detected a sudden flash of light as the star was torn apart. Over the following months, they watched the debris spiral into the black hole, creating a temporary glow visible across half the observable universe. This event is called a tidal disruption event. The tidal forces, similar to the ones that cause ocean tides on Earth due to the moon's gravity, were strong enough to shred a star. If a star can't survive, what chance does a human have? Let's return to the numbers. For a stellar mass black hole, roughly 10 times the mass of our Sun, the tidal forces become deadly at about 200 meters from the event horizon. You'd be stretched into a stream of atoms before you ever crossed the point of no return. Death would come quickly. For the supermassive black hole at our galaxy's center, the numbers change. The event horizon is so far from the center that the tidal forces there are weak. You could survive the crossing, but survival only delays the inevitable. As you continue falling inward, the gradient steepens. Within hours, maybe less, the stretching begins. And once it starts, there's no stopping it. But here's something even stranger. From your perspective, the experience might not feel like being pulled apart, at least not at first. Remember, you're in free fall. Everything around you falls at the same rate. Your body doesn't feel the pull of gravity directly. What you feel is the difference in pull across your body. At first, that difference feels like mild tension, a stretch, uncomfortable but not immediately painful. Then it intensifies. Your joints ache, your spine cracks, your skin tears. The tension becomes unbearable, and still you fall. In the final moments, you are no longer recognizably human. Your atoms stream toward the center in a thin filament, joining the mass of the black hole. Everything you were becomes part of the singularity. But what exactly is the singularity? What happens at the very center where all that matter collects? This is where our understanding ends. The equations break down. The physics fails. We are left with a mystery that challenges everything we think we know about reality. And the answer might rewrite the laws of the universe. Every path inside a black hole leads to the same destination, the singularity. A point at the center, where matter has been crushed beyond any limit we can calculate. Density becomes infinite. Curvature becomes infinite. The equations we use to describe the universe produce answers that make no sense. And that's the problem. When physicists say the singularity has infinite density, they're not describing something real. They're admitting that our mathematics has failed. The equations of general relativity, Einstein's masterpiece that describes gravity as the curvature of space and time, work beautifully everywhere else in the universe. They predict the bending of light, the expansion of space, the behavior of orbiting planets. But at the singularity, they collapse. This tells us something important: our understanding of physics is incomplete. Somewhere in the extreme conditions at the center of a black hole, the rules change, and we do not yet know the new rules. Here's what we think happens based on our best current theories. As matter falls inward, it gets compressed. The density increases. At some point, the density exceeds anything found in ordinary matter. Even neutron stars, where atoms are crushed so tightly that protons and electrons merge into neutrons, cannot compare. The matter inside a black hole reaches a state beyond neutrons, beyond quarks, beyond anything we have names for. Eventually, all that matter concentrates into a region smaller than an atom, perhaps smaller than a single particle. All paths through space and time curve so sharply that they converge on this point. Time itself, according to the equations, comes to an end, not in the sense that a clock stops ticking, but in the sense that there is no future beyond the singularity. It is a boundary, not just in space but in time. This is theoretical. No one has observed a singularity directly. By definition, we cannot. The event horizon prevents any information from escaping. Everything we know about the singularity comes from mathematics and educated guesses. But most physicists believe that the singularity as described by general relativity is not real. It is a sign that a new theory is needed. When you get answers like infinity, it usually means your equations are missing something. The missing piece is probably quantum mechanics. Quantum mechanics describes the behavior of matter and energy at the smallest scales, particles and waves, probabilities and uncertainties. At the singularity, where everything is compressed into an unimaginably small space, quantum effects must become important. But here's the frustrating part: we do not yet have a theory that combines quantum mechanics and gravity in a consistent way. The two pillars of modern physics refuse to work together at the singularity. This is one of the greatest unsolved problems in science. A theory of quantum gravity would explain what really happens at the center of a black hole. It might reveal that the singularity is not a point of infinite density, but something else entirely. Perhaps a tunnel to another region of space and time. Perhaps a new universe being born. Perhaps something we cannot yet imagine. Some researchers speculate that the singularity is where our universe ends and something new begins. Others think information that falls in might be preserved in ways we do not understand, encoded on the event horizon like words on a page. We do not know. And until we do, the singularity remains the ultimate mystery, a place where the universe hides its deepest secrets behind a veil we cannot lift. But black holes are not just the final destination for matter. They are also born in some of the most violent events the universe has ever witnessed. The death of a massive star is about to create something that will last for eons. Every black hole begins with destruction. An event so powerful it can outshine entire galaxies for a brief moment, scattering elements across light years and transforming a star into an object that defies comprehension. Let's start with a massive star, much larger than our own sun. Our sun is relatively modest and will end its life quietly, swelling into a red giant before shedding its outer layers and fading into a white dwarf. There will be no black hole, no explosion, just a slow, gentle fading away. But stars more than 20 times the mass of our sun live very different lives. They burn hotter, they burn faster, and when their fuel runs out, they do not fade, they explode. For millions of years, such a star fuses hydrogen into helium in its core. The energy from this fusion creates an outward pressure that balances the inward pull of gravity. The star remains stable, bright, and massive, but fusion doesn't stop at helium. Over time, helium fuses into carbon, carbon into oxygen, oxygen into silicon. Each stage burns faster than the last. The final stage, fusing silicon into iron, lasts only about a day, and then everything changes. Iron cannot fuse to produce energy, it absorbs energy instead. The moment the core fills with iron, the outward pressure vanishes. Gravity wins instantly. What happens next takes less than a second. The core collapses at a quarter of the speed of light. Layers of the star that took millions of years to build come crashing inward. The density skyrockets. Temperatures soar to billions of degrees. Then, the collapse halts as the matter reaches nuclear density, the point where particles resist being pushed any closer together. The infalling material rebounds off this dense core like a ball bouncing off a wall. A shock wave races outward through the star. This is a supernova. The explosion is beyond imagination. For a few weeks, a single dying star releases more energy than our sun will produce in its entire 10 billion year lifetime. The outer layers blast into space at tens of thousands of miles per second, carrying heavy elements forged in the final moments of the star's life. These elements, iron, gold, uranium, seed the universe with the building blocks of planets and people. But the core remains. If the original star was massive enough, that core cannot support itself, even at nuclear density. Gravity overwhelms everything. The core continues collapsing, shrinking past the point of no return until it forms a black hole, a region of space where matter is compressed so densely that escape becomes impossible. This isn't just theory. We have observed dozens of stellar black holes in our galaxy by watching how they affect nearby stars. When a black hole orbits close to a normal star, it pulls matter from its companion. That matter spirals inward, heats up, and emits X-rays we can detect from Earth. The masses of these stellar black holes range from about 5 to several tens of times the mass of our Sun. They are small compared to the giants at the centers of galaxies, but they are everywhere. Astronomers estimate that there are about 100 million of them wandering through the Milky Way. Most are invisible, pulling on nothing, revealing themselves to no one. You could be a few light years from one right now and never know. But not all stellar black holes form the same way. Some are born from mergers. Some might form from direct collapse without an explosion. And some have masses that challenge our current understanding. The smallest black hole ever found pushes the limits of what we thought possible. The final day of a massive star's life moves faster than anything else in its history. After millions of years of steady burning, the end comes in hours, and the actual collapse takes less than a second. Let's slow it down. The star has spent its life fighting gravity. Nuclear fusion in the core creates energy, and that energy pushes outward, balancing the tremendous weight of the outer layers. This balance has held for millions of years. But fusion is not forever. The fuel runs out in stages, each shorter than the last. Hydrogen burning lasts millions of years. Helium burning lasts hundreds of thousands. Carbon burning lasts centuries. Oxygen burning lasts months. Silicon burning, the final stage, lasts about a single day. When silicon fuses, it produces iron. And iron is the end of the road. Fusing iron does not release energy, it consumes it. The moment iron fills the core, the star's engine dies. What follows is catastrophic. Without fusion to create outward pressure, gravity has nothing to oppose it. The core begins to collapse, not slowly, not gently, but at nearly 70,000 miles per second. In less than a second, a core roughly the size of Earth compresses into a ball about 12 miles across. Try to picture that, a region larger than our planet, containing more mass than our sun, crushing down into something smaller than a city. The compression is so violent that electrons are forced into protons, creating neutrons. For a brief moment, the core becomes a neutron star, an object so dense that a single teaspoon weighs billions of tons. But if the original star was massive enough, even neutron pressure cannot hold. Gravity does not stop. It overwhelms the nuclear forces that keep particles apart. The collapse continues, accelerating past every barrier physics can offer. At some point, the collapsing matter crosses its own event horizon. A black hole is born. Meanwhile, the outer layers of the star are still falling inward, unaware that the core has already transformed into something inescapable. They crash into the forming black hole or rebound off the brief neutron star phase, creating a shockwave of unimaginable power. This shockwave tears through the star, heating the outer layers to temperatures where new nuclear reactions occur. Heavy elements form in the explosion itself: gold, platinum, uranium, all forged in seconds. The shockwave reaches the surface, and the star explodes outward. This is the supernova. From Earth, it appears as a new star in the sky, sometimes visible in daylight. Ancient astronomers recorded these events without understanding what caused them. But the core is gone. Where there was once a furnace of nuclear fire, there is now only silence. A black hole sits in the debris, invisible except for its gravity. Matter that falls too close spirals in. Energy radiates from the infalling material, but the black hole itself reveals nothing. This entire sequence, from core collapse to supernova to black hole formation, happens in seconds. The star spent millions of years building its layers. Gravity destroyed them almost instantly. Yet, not every massive star's death results in a black hole. Some leave behind neutron stars instead. The difference comes down to mass, and that difference creates a puzzle. There's a gap in the masses where black holes seem not to exist, and scientists are still debating why. But before we explore that mystery, let's look at the other extreme, the smallest black hole ever confirmed, which challenges everything we thought we knew about how compact these objects can be. When astronomers announced the discovery in 2020, it sparked immediate debate. They had found a black hole with only about 3 times the mass of our Sun, barely larger than the heaviest neutron stars, sitting right at the edge of what should be possible. The system was given a technical name, but the discovery itself was unforgettable. For decades, scientists believed there was a clear boundary between neutron stars and black holes. Neutron stars, the crushed cores of dead stars, could reach about 2 to 2.5 solar masses before collapsing further. Black holes, on the other hand, seemed to start around 5 solar masses. The zone in between was strangely empty. This new discovery landed right in that gap. The black hole orbits a red giant star about 1/500 light-years from Earth. By studying how the red giant wobbles, astronomers calculated the mass of its invisible companion, 3 solar masses. And the companion was too compact and too dark to be anything other than a black hole. At that mass, the black hole would be tiny. Its event horizon would measure only about 12 miles across, small enough to fit inside a medium-sized city. Yet, within that space lies more mass than 3 of our suns combined. This finding challenges some theories about how black holes form. The traditional story says massive stars explode in supernovae and leave behind black holes with masses starting around 5 times that of our Sun. Below that, you get neutron stars instead. The gap between 2 and 5 solar masses seemed like a rule of nature. But this discovery suggests the gap may not be as empty as we thought. Either some black holes form through unusual processes that produce lower masses, or our understanding of stellar explosions needs revision. One possibility is that some stars collapse quietly. Instead of exploding in a brilliant supernova, they might implode directly into black holes without much fanfare. This could produce black holes at the lower end of the mass range. Another possibility involves binary systems. If 2 neutron stars orbit each other and eventually merge, the combined mass could exceed the limit and collapse into a small black hole. Gravitational wave detectors have already observed such mergers. The remnants would be lightweight black holes just above the neutron star limit. What makes this discovery even more striking is how close the object is. 500 light-years sounds like a vast distance. But in galactic terms, it's practically next door. If small black holes like this one are common, there could be many more lurking nearby, invisible against the background of space. Finding them is difficult. Small black holes do not emit light. They do not glow unless matter falls into them. If one drifts through empty space, pulling on nothing, we would never detect it. Only when a black hole has a companion, a star it can gravitationally influence, do we have a chance to measure its effects. Astronomers estimate that for every black hole we have found, thousands more remain hidden. The Milky Way could be teeming with these small, silent remnants. They drift among the stars, carrying the mass of collapsed suns, revealing themselves only through subtle gravitational tugs. But small black holes are only part of the story. Some black holes live in pairs, locked in a gravitational dance that will one day end in catastrophe. 2 predators circling each other, neither willing to let go. In the darkness between stars, 2 black holes spiral toward each other. They have been dancing for millions of years, maybe billions. Each orbit brings them slightly closer. Each pass drains a little more energy from their motion, and one day the dance will end. When it does, the collision will shake the fabric of space and time itself. Binary black hole systems form in several ways. Sometimes 2 massive stars are born together, orbiting each other from the beginning. When both stars die and collapse, they leave behind 2 black holes still locked in mutual orbit. The same gravitational bond that held the stars together now holds their remnants. Other times, black holes find each other later in dense environments like globular clusters, where hundreds of thousands of stars crowd into a region only a few dozen light-years across. Black holes can sink toward the center and capture each other through close encounters. These pairings are chaotic, formed by chance rather than shared birth. However they come together, the result is the same: 2 of the most extreme objects in the universe, bound by gravity, falling toward a common fate. Here's what makes binary black holes special. As they orbit, they lose energy by emitting gravitational waves, ripples in space and time itself, spreading outward at the speed of light. We can't see them with telescopes, but we can detect them with instruments that measure the stretching and squeezing of space as the waves pass. The energy carried by gravitational waves comes from the orbit itself. As energy leaves, the black holes spiral closer. The process is incredibly slow at first. 2 black holes separated by millions of miles might take billions of years to merge. But the closer they get, the faster they lose energy. The final spiral accelerates rapidly. In the last seconds before collision, the black holes whip around each other at a significant fraction of the speed of light. They complete dozens of orbits per second. The gravitational waves intensify, rising in frequency and amplitude. Scientists call this the chirp, because if you converted the waves to sound, it would resemble a rising tone that ends abruptly. Then, impact. The two event horizons merge. The combined black hole shudders and distorts briefly, assuming a lumpy, unstable shape. Within milliseconds, it settles into a smooth, spinning configuration. The ring-down phase sends out final gravitational waves. As the new black hole achieves equilibrium, the energy released is staggering. When two black holes of 30 solar masses each collide, roughly 3 solar masses of material convert entirely into gravitational wave energy. In that fraction of a second, the merger radiates more power than all the stars in the observable universe combined. Not as light, but as gravity. We first detected this cosmic phenomenon in 2015. Two black holes, one about 36 times the mass of our Sun and the other about 29, merged roughly 1.3 billion light-years away. The gravitational waves from their collision traveled across the universe, weakening as they spread, until they finally reached Earth as a faint vibration, so subtle it stretched and compressed our planet by less than the width of a proton. Yet, our instruments were sensitive enough to catch it. That moment marked the dawn of gravitational wave astronomy. Since then, scientists have detected hundreds of binary black hole mergers. Each one reveals new details about how these systems form, how black holes spin, and how gravity behaves under the most extreme conditions. But there are still mysteries. The masses we detect sometimes fall into ranges that our theories struggle to explain. Something unexpected is happening with the so-called middleweight black holes. When astronomers started counting black holes, they expected to find them at all sizes. Small ones from modest stellar deaths, large ones from massive stellar deaths, a smooth distribution from a few solar masses up to dozens. Instead, they found gaps. The lower mass gap sits between roughly 2 and 5 solar masses. Neutron stars top out around 2.5 solar masses, while black holes seem to start around 5. For years, the zone between appeared empty. We discussed one recent exception, but it remains unusual. Most stellar black holes cluster above 5 solar masses. The upper mass gap is even stranger. It stretches from roughly 50 to 130 solar masses. Theory says black holes should not form in this range from normal stellar evolution. The reason has to do with how massive stars die. When a star's core becomes iron, it collapses. But for extremely massive stars, something different happens first. Before iron forms, the core reaches temperatures where photons convert into pairs of electrons, and their antimatter counterparts, positrons. This pair production removes pressure support from the core, triggering an early collapse. The collapse releases energy that ignites explosive oxygen and silicon burning. Instead of forming a black hole, the entire star blows apart. Nothing remains, no neutron star, no black hole, just an expanding cloud of debris. This is called a pair instability supernova. It happens for stars that would have produced black holes between roughly 50 and 130 solar masses. The star destroys itself so completely that nothing survives. Above 130 solar masses, the explosion cannot unbind the star. Gravity wins. A black hole forms directly, skipping the gap. Below 50 solar masses, normal supernovae produce black holes without triggering pair instability. So theory predicts a gap, and for years, observations agreed. The black holes we found clustered below 50 solar masses, with a few exceptional giants above 130. Then gravitational wave detectors started finding anomalies. In 2019, a merger was detected involving a black hole of about 85 solar masses, right in the forbidden zone. The discovery forced theorists to reconsider. Maybe some black holes in the gap form through mergers of smaller black holes. If 230 solar mass black holes combine, the result would sit in the previously forbidden range. Hierarchical mergers, where the products of earlier mergers combine again, could populate the gap over time. Another possibility involves unusual stars. Some stars in the early universe, containing fewer heavy elements than modern stars, might have behaved differently. They could have lost less mass to stellar winds, retained more material, and collapsed into black holes within the gap. Or perhaps our models of pair instability are incomplete. The boundaries of the gap depend on nuclear physics at extreme temperatures. Small changes in those calculations could shift the edges. What we know is that the gap exists for most black holes, but it is not absolute. Some objects cross the boundaries, and those exceptions might tell us more about black hole formation than all the normal cases combined. But stellar mass black holes, even the mysterious ones, are tiny compared to what lurks between the extremes. There is an entire class of black holes we struggle to find, massive enough to dwarf stellar remnants, small enough to hide from our surveys. These are the missing, middle children of the black hole family. Between the stellar black holes formed from dying stars and the supermassive giants anchoring galaxies lies a vast unknown. Black holes with masses from 100 to 100,000 times that of our Sun should exist. Physics allows them. Logic suggests they must be out there, yet we have found only a handful of candidates. Intermediate mass black holes are the most mysterious members of the black hole family. They are too large to form from single stellar collapses. They are too small to be the ancient monsters at galactic centers. They occupy a middle ground that remains frustratingly dark. Why do we expect them to exist? The argument goes like this. Supermassive black holes did not appear fully formed. They had to grow from something smaller, seeds. Those seeds could have been intermediate mass black holes that merged and fed their way to enormity over billions of years. Without the middle step, we struggle to explain how the giants got so big so fast. But finding intermediate mass black holes is hard. They do not form from ordinary stellar deaths, so they are not scattered everywhere like stellar remnants. They are not massive enough to dominate galactic cores like supermassive black holes. They hide. One way to form them involves dense stellar environments. Picture a globular cluster, a spherical swarm of hundreds of thousands of stars packed into a region, maybe 100 light years across. At the center, stars crowd together, collisions happen. Massive stars merge into massive stars that collapse directly into black holes larger than any single star could produce. Once formed, an intermediate mass black hole at the center of a cluster would sink deeper due to dynamical friction, interacting gravitationally with surrounding stars. It would continue to grow, swallowing stars and smaller black holes that wander too close. Over billions of years, it could reach thousands of solar masses. There's also another possible path to creating these elusive intermediate mass black holes. In dense star clusters, black holes can collide and merge repeatedly. Imagine a crowded environment where dozens or even hundreds of stellar mass black holes drift toward the center, pulled by gravity. As they interact, some form pairs and merge, creating larger black holes. Over time, this process can repeat, with each new merger producing a black hole bigger than the last. This runaway merger scenario could, in theory, build up black holes in the intermediate mass range, hundreds or even thousands of times the mass of our Sun. There's even speculation that some intermediate mass black holes might be primordial, formed in the earliest moments after the Big Bang, through mechanisms unrelated to stars at all. These ancient relics would be scattered throughout the universe, invisible unless they happen to interact with other matter. So, where are the candidates? The strongest evidence comes from a source called HLX-1, located in a galaxy about 290 million light-years away. This object emits X-rays consistent with a black hole actively consuming matter. By analyzing how the brightness changes and estimating the temperature of the infalling material, researchers calculated a mass around 20,000 times that of our Sun, not supermassive, not stellar, but intermediate. Another candidate appeared in gravitational wave data from 2019. The merger produced a black hole of roughly 142 solar masses, still below the traditional intermediate threshold of 1,000 solar masses, but right at the edge. Some consider it the first confirmed intermediate mass black hole formed from a collision we witnessed. Others remain skeptical. Measuring the masses of distant objects involves significant uncertainty. Some candidates might be misidentified. Some might have explanations that do not involve black holes at all. What we can say is that the intermediate mass range is not empty. Candidates exist, but compared to the millions of stellar black holes in our galaxy and the supermassive ones in every large galaxy, intermediate mass black holes remain rare, or at least rarely detected. The search continues. New telescopes, new gravitational wave detectors, and new techniques for finding invisible objects through their gravitational effects are all being developed. Somewhere in the darkness, the missing link waits to be found. Scattered around our galaxy are roughly 150 ancient star cities, globular clusters, spherical collections of hundreds of thousands of stars bound together by gravity, orbiting the Milky Way like satellites. They are among the oldest structures in the universe, formed billions of years ago when the cosmos was young, and they might be hiding exactly what we are looking for. Globular clusters are strange places. The stars inside them are packed together at densities unimaginable in our neighborhood. Near the center of a dense cluster, stars might be separated by only a fraction of a light year. In our region of the galaxy, the nearest star is over 4 light-years away. Cluster cores are crowded by comparison. This crowding changes everything. Stars interact. They pass close to each other, exchanging energy, altering orbits. Sometimes they collide outright, merging into more massive objects. In such environments, unusual things can form. Here's why clusters matter for intermediate mass black holes. When massive stars die, they leave behind stellar black holes. In a normal galaxy, these black holes drift apart, rarely encountering each other. But in a cluster core, black holes sink toward the center through a process called mass segregation. Heavy objects lose energy to lighter stars and fall inward. Given enough time, black holes accumulate in the densest region. Once clustered together, black holes can interact. They form binaries. They merge. Each merger produces a slightly larger black hole. If this happens repeatedly over billions of years, the product could grow into the intermediate mass range. Computer simulations support this scenario. They show that dense clusters can produce black holes of hundreds or even thousands of solar masses through sequential mergers. The most massive black hole dominates the core, continuing to grow by swallowing smaller black holes and occasionally entire stars that wander too close. Direct evidence is harder to obtain. We cannot see intermediate mass black holes directly. We can only infer their presence through their effects on surrounding stars. One approach measures the velocities of stars near the cluster center. If an intermediate mass black hole lurks there, its gravity would accelerate nearby stars to higher speeds than expected from the visible mass alone. Astronomers have tried this technique on several clusters with mixed results. Some show hints of excess mass, others do not. Another approach looks for X-ray emissions. If an intermediate mass black hole captures gas from passing stars, that gas heats up as it spirals inward, emitting X-rays. Several globular clusters associated with our galaxy and nearby galaxies have X-ray sources that could be intermediate mass black holes feeding at low rates. The emissions are faint, making definitive identification difficult. Then there is the gravitational wave approach. When intermediate mass black holes merge with stellar black holes, they produce gravitational waves in a frequency range that current detectors can observe. The more mergers we detect, the better we can estimate how common intermediate mass black holes are in clusters. So far, the picture is incomplete. Some clusters probably host intermediate mass black holes, others might not. The formation efficiency depends on cluster density, age, and history. Not every cluster produces a monster, but the search has intensified. Every gravitational wave detection, every X-ray survey, every careful measurement of stellar velocities brings us closer to understanding where intermediate mass black holes live. And understanding where they live helps explain how the largest black holes in the universe came to be. Imagine the process of building up an intermediate mass black hole in a dense star cluster. It starts with the deaths of massive stars, each leaving behind a stellar mass black hole. Over time, these black holes drift toward the cluster's core, pulled by gravity and slowed by interactions with lighter stars. As they gather in the center, their chances of encountering one another increase. Some form pairs and merge, creating larger black holes. Each merger releases a burst of gravitational waves, carrying away energy and allowing the new black hole to settle deeper into the cluster's heart. This process can repeat over and over. The merged black hole may find another partner, and the cycle continues. In computer simulations, this runaway merger scenario can produce black holes with hundreds or even thousands of times the mass of our Sun within a few billion years. The most massive black hole becomes the dominant object in the cluster, swallowing smaller black holes and even the occasional star that strays too close. But there are challenges to this process. Each time two black holes merge, the resulting object receives a kick from the asymmetric emission of gravitational waves. Sometimes, this kick is strong enough to eject the black hole from the cluster entirely, ending the chain of mergers. The likelihood of ejection depends on the masses and spins of the merging black holes, as well as the density of the cluster. In some cases, the runaway growth is cut short, and the cluster is left with a moderately massive black hole or none at all. Despite these obstacles, the runaway merger scenario remains one of the leading explanations for the formation of intermediate mass black holes in the present universe. It doesn't require any single extraordinary event, just time, a dense environment, and a steady supply of stellar mass black holes. Over billions of years, these ingredients can produce black holes that bridge the gap between the stellar and supermassive classes. Once an intermediate mass black hole forms, it can continue to grow by consuming stars, gas, and smaller black holes. The chain doesn't have to stop. Given enough time and fuel, an intermediate mass black hole could eventually become a supermassive one, especially if it migrates toward the center of a galaxy and finds itself in a region rich with material to feed on. We have already found at least one candidate that might show this process in action. About 290 million light-years from Earth, in a galaxy known as ESO 4349, astronomers have identified an X-ray source called LX1. This object flares and dims over weeks and months, suggesting it is actively consuming material. It sits not at the galaxy's center, but off to the side, embedded in what appears to be a small star cluster. This cluster might be the stripped core of a dwarf galaxy that was swallowed by the larger host. What makes HLX1 special is its brightness and behavior. Ordinary stellar mass black holes eating gas from companion stars produce X-rays. But there's a limit to how bright they can get. A black hole can only consume material so fast before radiation pressure pushes incoming gas away. This limit, called the Eddington limit, depends on mass. The more massive the black hole, the higher the limit. HLX-1 is too bright to be a stellar mass black hole eating at its maximum rate. The X-ray luminosity requires either a black hole far more massive than any stellar remnant, or a stellar black hole, somehow breaking the rules. When researchers modeled the emission, they concluded that HLX-1 hosts a black hole of approximately 20,000 solar masses. That places it firmly in intermediate mass territory, not as large as the millions or billions of solar masses found in galaxy centers, but far beyond the range of stellar remnants. The fact that HLX-1 sits in a star cluster supports the idea that it may have formed through runaway mergers in a dense environment, or perhaps it was the central black hole of a dwarf galaxy that was later cannibalized by a larger one. HLX-1's outbursts are thought to be caused by a companion star in an elongated orbit. Each time the star swings close, it loses some material to the black hole, triggering a flare. Over time, the companion may be completely consumed, and the black hole will go quiet, becoming invisible once more. This is the frustrating reality of hunting intermediate mass black holes. We can only see them when they are feeding. When the fuel runs out, they vanish into darkness. How many quiet intermediate mass black holes drift through galaxies, too far from any star to consume, invisible to all our instruments? We do not know, but HLX-1 proves they exist. At least one intermediate mass black hole is out there, caught in the act of eating. Where there is one, there must be others. The question now is how many, and whether they can help explain the origins of the true monsters, the black holes that anchor entire galaxies. At the center of nearly every large galaxy sits something that should be impossible, a black hole so massive that it contains not thousands, not millions, but sometimes billions of times the mass of our Sun, compressed into a region smaller than our solar system. These are the supermassive black holes, the anchors of galaxies, the engines of the brightest objects in the universe. And we still do not fully understand how they exist. The smallest supermassive black holes weigh in at around 100,000 to 1,000,000 solar masses. These sit at the centers of dwarf galaxies and small spirals. The largest exceed 10 billion solar masses. These monsters dominate giant elliptical galaxies, warping space so severely that time itself flows differently near their influence. Our own galaxy, the Milky Way, is home to a relatively modest supermassive black hole called Sagittarius A. With a mass of about 4 million times that of our Sun, it's still enormous by any standard. Yet it's considered small compared to the true giants found in other galaxies. The discovery of supermassive black holes was a gradual process. In the 1960s, astronomers began to notice objects called quasars, points of light that looked like stars but shone with the energy of entire galaxies, even though they appeared tiny in the sky. Nothing known could produce so much energy in such a small region, except for matter falling into an incredibly massive black hole. Later, as telescopes improved, it became clear that most large galaxies harbor a central black hole, even those that don't shine as brightly as quasars. These quiet galaxies, like our own, still contain dormant giants. They may not be feeding much right now, so they don't blaze with energy. But their mass is there, detectable through their influence on nearby stars. Measuring that influence takes patience and precision. Stars near the galactic center orbit the black hole, and by tracking their paths over years, astronomers can calculate the mass they must be circling. For the Milky Way, this technique has produced extraordinary data. Some stars, like the famous S2, swing around Sagittarius A at thousands of miles per second, completing orbits in as little as 16 years. The speed and shape of these orbits reveal the central mass. This work was so groundbreaking that it earned the Nobel Prize in Physics in 2020. Direct proof of a supermassive black hole through the motion of stars. But knowing that supermassive black holes exist doesn't explain how they formed. The universe is about 13.8 billion years old. That sounds like a long time, but building a billion solar mass black hole from scratch is a daunting task. If a black hole consumed matter at the maximum possible rate since the universe began, it would still struggle to reach the masses we observe. Even more puzzling, we find supermassive black holes in the very early universe, quasars shining when the cosmos was less than a billion years old. Their black holes were already enormous. How did they grow so fast? This is one of the biggest open questions in astrophysics. Several theories compete to explain it. One idea is that the first black holes were born massive, collapsing directly from enormous clouds of gas without forming stars first. These direct collapse black holes could start out with tens of thousands of solar masses, giving them a head start. Another theory suggests that intermediate mass black holes formed through runaway mergers in dense star clusters, then sank to galactic centers and merged again, building up mass over time. Some researchers even propose that exotic physics in the early universe allowed black holes to grow faster than we expect. Whatever the answer, the scale of these objects is staggering. Supermassive black holes are not just large. They are the dominant gravitational force in their region of space, shaping the galaxies around them. Their gravity influences star formation, stirs up gas, and can even regulate the growth of the galaxy itself. The presence of a supermassive black hole defines the center of a galactic system. Building a supermassive black hole is a problem of both time and supply. You need an enormous amount of mass to fall into a single location, and you need it to happen faster than conventional physics seems to allow. The leading theories all try to solve this puzzle in different ways. The first possibility is that supermassive black holes grew from stellar seeds. Imagine the early universe filled with massive stars, hundreds of times the mass of our Sun. These first stars lived fast and died young, leaving behind black holes of perhaps 100 to 1,000 solar masses. If those seeds then fed continuously, consuming nearby gas at high rates, they could grow over billions of years into supermassive black holes. The problem is the rate. There's a maximum speed at which a black hole can consume matter, set by the balance between infalling material and the pressure of outgoing radiation. Eating at this maximum rate for 13 billion years gets you to maybe a few 100 million solar masses. Impressive, but not enough to explain the billion solar mass giants we see in the early universe. So, something else must be happening. The second possibility is direct collapse. In the early universe, some regions contained enormous clouds of primordial gas. If these clouds collapsed without fragmenting into stars, they could fall directly into black holes of 10,000 to 100,000 solar masses in a single event. No stellar phase, no supernova, just rapid gravitational collapse into something already large. Direct collapse requires special conditions. The gas cloud must be warm enough to avoid breaking up into stars, and it must lack heavy elements that promote cooling and fragmentation. Computer simulations show this can happen, but only in specific environments. If direct collapse worked, it would produce seed black holes large enough to grow into supermassive ones within the available time. A third possibility involves mergers. Intermediate mass black holes formed through runaway collisions in dense star clusters could sink toward galactic centers and combine. Each merger doubles the mass, and after enough generations, you reach supermassive territory. This path is supported by gravitational wave observations. We know black holes merge, and we know the products are larger. The question is whether mergers happened frequently and efficiently enough in the early universe to build supermassive black holes quickly. There might not be a single answer. Different supermassive black holes might have formed through different channels, some from direct collapse, some from rapid accretion, some from mergers, and some from combinations of all three. New telescopes, like the James Webb Space Telescope, are now probing the first billion years of cosmic history, searching for clues. Early results have already revealed surprisingly large black holes shining in the infant universe, challenging our models and pushing us to rethink what's possible. Whatever their origin, supermassive black holes have been shaping galaxies for billions of years. Their gravity influences the orbits of stars, the flow of gas, and even the rate at which new stars are born. When a supermassive black hole is actively feeding, it can become the brightest object in the universe, a quasar. These cosmic lighthouses shine with the energy of trillions of suns, visible across billions of light years. But most of the time, even the largest black holes are quiet, waiting for the next meal. At the heart of our own galaxy, Sagittarius A sits quietly 26,000 light-years from Earth, hidden behind clouds of dust and gas. For decades, astronomers suspected something massive lurked at the galactic center. Radio observations in the 1970s detected a compact source of emission far too energetic for any ordinary object. But it was only by tracking the orbits of stars near the center, using infrared telescopes that could see through the dust, that the true nature of Sagittarius A was revealed. One star, S2, completes an orbit around Sagittarius A every 16 years. At its closest approach, it sweeps within just a few billion miles of the black hole, moving at nearly 3% the speed of light. The orbit is precise, and the mass required to produce such motion is undeniable. 4 million solar masses concentrated in a volume no larger than the orbit of Mercury. There is no other explanation. Only a supermassive black hole fits the data. In 2022, the Event Horizon Telescope produced an image of Sagittarius A itself. Not the black hole, which emits no light, but the glowing ring of hot gas swirling around it. The shadow in the center marks the event horizon, the boundary from which nothing returns. That image confirmed what decades of stellar tracking had implied: a supermassive black hole sits at the center of our galaxy. It is real. It is there, and it has been anchoring the Milky Way for billions of years. Yet Sagittarius A is quiet. Unlike the blazing quasars powered by actively feeding black holes in distant galaxies, our black hole consumes very little. The gas around it trickles in slowly, emitting faint radiation. If the Milky Way's black hole suddenly started feeding at full capacity, it would outshine the entire galaxy. For now it rests, but this was not always the case. Evidence suggests that Sagittarius A was more active in the past. X-ray echoes bouncing off nearby gas clouds indicate powerful flares occurred within the last few hundred years. Bubbles of hot gas extending above and below the galactic plane, detected by gamma-ray telescopes, suggest enormous outbursts millions of years ago. The black hole wakes occasionally. When enough gas falls in, it lights up. Then it settles down again, waiting for the next meal. Living 26,000 light-years from a 4 million solar mass black hole might sound frightening, but the distance is so vast that Sagittarius A poses no threat. Its gravity dominates only within a few light-years of the center. Out here in the galactic suburbs, we orbit peacefully, held by the combined mass of billions of stars. Still, it is humbling to know that our entire galaxy pivots around a point of darkness, a place where spacetime curves so steeply that nothing survives the inward journey. But 4 million solar masses is modest by supermassive standards. Some black holes make Sagittarius A look tiny. We are about to meet one that was imaged before our own. On April 10, 2019, humanity saw the unseeable for the first time. A glowing ring of fire surrounding a dark shadow. The first direct image of a black hole's event horizon. proof that these objects exist exactly as Einstein's equations predicted over a century ago. The black hole sits at the center of Messier 87, a giant elliptical galaxy roughly 55 million light-years from Earth. It weighs between 6 and 12 billion solar masses, over 1,500 times more massive than the black hole at the center of our own galaxy. Capturing that image required building a telescope the size of Earth itself. No single telescope could do it. The black hole is so far away that, despite its enormous size, it appears incredibly small in the sky. Resolving its shadow required a resolution sharper than any instrument in history. The solution was the Event Horizon Telescope, a network of radio dishes spanning the entire planet, from Hawaii to Spain to the South Pole. By linking these telescopes together and observing the same target simultaneously, astronomers created a virtual telescope with an effective diameter equal to Earth. The technique, called Very Long Baseline Interferometry, combines the data mathematically to achieve resolution impossible for any single dish. Even with this power, the observation was extraordinarily difficult. The team spent over a decade planning. They waited for weather to cooperate at all sites simultaneously. They recorded so much data that it had to be shipped on hard drives, because internet transfer would have taken too long. They developed new algorithms to combine the fragmented observations into a coherent image. What emerged from that effort changed astronomy. The image shows a bright ring of emission surrounding a dark central region. The ring is gas superheated to billions of degrees as it spirals toward the black hole. It glows in radio waves, which is why radio telescopes were necessary. The dark shadow in the center is not the black hole itself. It is the region where light has been captured, unable to escape. The size of that shadow matches the predictions of general relativity almost perfectly. Einstein's equations, written in 1915 without any knowledge of black holes as astrophysical objects, correctly described what we would see a century later. But there's more to the story than just confirmation. The image of Messier 87's black hole revealed subtle details that tell us about the nature of these cosmic giants. Notice how one side of the ring appears brighter than the other. This isn't a trick of the camera. It's a direct result of the gas orbiting the black hole at incredible speeds, close to the speed of light. The side of the ring where the gas is moving toward us appears brighter, due to a phenomenon called relativistic beaming, while the side moving away is dimmed. This brightness difference gives us clues about the direction and speed of the swirling matter, and even hints at the spin of the black hole itself. Most supermassive black holes are thought to be spinning, some at rates close to the maximum allowed by the laws of physics. Over billions of years, as they consume matter and merge with other black holes, they accumulate angular momentum. A spinning black hole doesn't just sit passively in space, it drags spacetime around with it, twisting the very fabric of the universe in a process called frame dragging. This effect is impossible to observe anywhere else in the cosmos, but near a black hole, it becomes significant. 3 years after the first image, the Event Horizon Telescope turned its attention to our own galactic center. Imaging Sagittarius A was even more challenging than Messier 87's black hole. Although it's much closer, it's also much smaller, so the gas around it orbits much faster. Features change in minutes rather than days, making it difficult to capture a stable image. The team had to develop new techniques to piece together a picture from rapidly shifting data. The result, released in 2022, was another glowing ring and dark shadow, further confirmation that the predictions of general relativity hold true. Even in the most extreme environments, both images represent triumphs of human ingenuity. We cannot visit black holes or send probes into their depths, but we can build instruments capable of seeing across millions of light years and resolving objects smaller than our solar system. Yet, even Messier 87's black hole is not the largest. There are black holes so massive that the term supermassive barely does them justice. At some point, astronomers began to use the word ultramassive to describe these titans. Black holes with more than 10 billion times the mass of our Sun. Consider the scale for a moment. Our Sun is about 60,000 miles in diameter. A stellar mass black hole of 10 solar masses would have an event horizon roughly 37 miles across. Sagittarius A, at 4 million solar masses, has an event horizon about 14 million miles in diameter, still smaller than the orbit of Mercury. But an ultramassive black hole of 40 billion solar masses would have an event horizon over 750 billion miles wide. That's more than 125 times the distance from the Sun to Pluto. Light would take weeks to cross from one side to the other. You could fit our entire solar system inside and still have room to spare. These are not objects in any ordinary sense. They are regions where gravity has completely taken over, dominating everything nearby. Where do ultramassive black holes live? They tend to sit at the centers of the largest, oldest galaxies, giant ellipticals formed from repeated mergers over billions of years. Each merger brings more mass to the central black hole, and each consumed galaxy contributes its own black hole to the final total. Over time, this process builds monsters that outweigh entire galaxies. The largest confirmed ultramassive black holes exceed 40 billion solar masses. One candidate, at the center of a galaxy called Holmberg 50A, may hold approximately that much mass. Another, powering the quasar known as Town 618, might exceed 60 billion solar masses. At these scales, the black holes outweigh most galaxies. The Milky Way contains about 200 billion stars, but most of that mass is spread across a disk 100,000 light-years wide. An ultramassive black hole compresses a comparable amount of mass into a region you could cross in weeks at the speed of light. But there appears to be a limit. Theoretical calculations suggest that black holes cannot grow indefinitely. Eventually, they consume all available matter in their vicinity, and without fresh fuel, growth stops. The maximum possible mass depends on the age of the universe and the availability of gas, but estimates suggest black holes cannot exceed about 100 billion solar masses through normal accretion. Some researchers believe we have already found black holes near this limit. If so, the largest black holes in the universe today are as big as they will ever get, waiting in darkness for the slow decline that will eventually claim them. Before they fade, though, they put on quite a show. One ultramassive black hole shines brighter than everything else in the known universe. Imagine an object so luminous it outshines 140 trillion stars, with that brilliance pouring from a region smaller than our solar system. This is Town 618, a quasar, a cosmic beacon, and a challenge to everything we thought we understood about the limits of black holes. Located nearly 11 billion light-years from Earth, Town 618 appears as a faint blue point in most telescopes. For decades, astronomers thought it was a peculiar star in our own galaxy. Only later did they realize it was a quasar, powered by a black hole with an estimated mass of 40 to 66 billion suns. Even the lower estimate makes it one of the heaviest black holes known. The higher estimate would place it among the absolute largest. But it's not just the mass of Town 618 that makes it extraordinary, it's how actively it feeds. Surrounding the black hole is a swirling disk of superheated gas, spiraling inward at incredible speeds. As this material falls, it releases gravitational energy as light, making Tau 618 shine with the luminosity of 140 trillion suns. That's more light than most entire galaxies produce. The glare is so intense that the host galaxy itself is hidden from view. All we see is the blinding beacon of the quasar. The event horizon of Town 618 is vast. If its mass is at the higher end of estimates, the boundary from which nothing can escape would stretch more than 1/300 times the distance from Earth to the Sun. Light would take days to cross from one side to the other. Dozens of planetary systems like ours could fit inside with room to spare. Yet, for all its size and power, TON 6/18 is unreachable. The light we see today left that region over 10 billion years ago, when the universe was young and galaxies were still assembling. Whatever TON 6/18 looks like now, we won't know for another 10 billion years. This is a humbling reminder when we observe distant quasars. We're looking into the deep past. The objects we study may have changed dramatically, or even disappeared since their light began its journey. We are cosmic archaeologists, piecing together the history of the universe from ancient signals. TON 6/18 represents an extreme, a black hole near the upper limit of possible mass, feeding at the upper limit of possible rate, shining at the upper limit of possible brightness. It's the universe pushed to its edge. But even the brightest quasar needs fuel, and to understand how black holes shine, we need to look at what happens to matter as it approaches the point of no return. Nothing falls straight into a black hole. Matter spirals inward, forming a flattened disk called an accretion disk. This is where destruction becomes energy. As gas and dust approach the black hole, they carry angular momentum, which keeps them from plunging directly in. Instead, they settle into orbit, forming a disk that gradually loses energy through friction and collisions. The inner regions of the disk orbit faster than the outer regions, creating shear and turbulence. As particles collide, they heat up, and the temperature in the innermost part of the disk can reach millions or even billions of degrees. At these temperatures, the gas glows intensely, emitting radiation across the electromagnetic spectrum, from radio waves to visible light, ultraviolet, X-rays, and even gamma rays. This is how black holes become visible, not from the black hole itself, which emits nothing, but from the destruction of matter trying to fall in. The process is incredibly efficient. Up to 30% of the infalling mass can be converted into energy, compared to less than 1% for nuclear fusion in stars. This efficiency explains why quasars can outshine entire galaxies. The structure of an accretion disk is layered. The outer regions are cooler, emitting mostly infrared and visible light. Moving inward, the temperature rises, and the emission shifts to ultraviolet and X-rays. The innermost region, just outside the event horizon, produces the highest energy radiation. Some disks even generate gamma rays from processes near the black hole. But accretion disks are not calm places. They are turbulent, with magnetic fields threading through the gas, twisting and reconnecting. Instabilities develop, and clumps of material can fall inward unpredictably. The brightness of an accreting black hole can fluctuate over days, hours, or even minutes as conditions in the disk change. Above and below the disk, powerful winds can be launched outward by radiation pressure. These outflows carry energy and matter back into the surrounding galaxy, influencing star formation and the chemical evolution of the host. In the most extreme cases, something even more dramatic happens. Jets of material, accelerated to nearly the speed of light, shoot out perpendicular to the disk. These jets can extend for millions of light years, carrying energy far beyond the galaxy that produced them. Not all actively feeding black holes produce jets. The conditions seem to require both rapid spin and the right magnetic field geometry. Only about 30% of active galactic nuclei are radio loud, meaning they have powerful jets. The rest are radio quiet, with little or no jet emission. Understanding why some black holes launch jets and others do not remains an open question. But spin and magnetic fields are likely key factors. Jets are among the largest structures any black hole creates. The galaxy Messier 87, home to the black hole imaged in 2019, has a jet visible in optical telescopes stretching nearly 5,000 light-years from the core. In radio observations, the structures extend much farther, inflating enormous lobes of hot gas in the surrounding space. These lobes represent the accumulated energy of millions of years of jet activity. Jets influence their environments profoundly. The energy they carry heats surrounding gas, preventing it from cooling and forming stars. In galaxy clusters, jets from central black holes can regulate the entire thermal state of the system. Without jets, the gas would cool, collapse, and form huge numbers of new stars. With jets, the gas stays hot and diffuse. This feedback loop connects the smallest scales, the immediate vicinity of a black hole, to the largest, the evolution of entire galaxy clusters. A single object smaller than our solar system can control the fate of millions of light-years of space. Black holes, once thought to be simple cosmic traps, are now seen as engines that shape the universe on every scale. The influence of black holes doesn't stop at shaping galaxies or launching jets. They also warp time itself. If you stood near a black hole, your own clock would tick normally, you'd feel no difference. But to a distant observer, your time would appear to slow down. This is gravitational time dilation, a real effect predicted by Einstein's theory of general relativity and confirmed by experiments. The stronger the gravity, the slower time passes relative to regions with weaker gravity. We see this effect on Earth with satellites. Their clocks tick slightly faster than those on the ground, and GPS systems must account for this to remain accurate. Near a black hole, this effect becomes extreme. As you approach the event horizon, the curvature of spacetime increases dramatically. To someone watching from far away, you would seem to freeze at the edge, your image fading and red shifting into darkness as the light you emit stretches to longer and longer wavelengths. From your own perspective, you would fall through the horizon in a finite time, experiencing nothing unusual at the crossing. But if you could look back, you'd see the universe outside racing ahead, stars aging, galaxies evolving, the cosmos moving toward its distant future while you drift toward your end. Inside the event horizon, the very nature of space and time changes. The direction toward the singularity becomes like time itself, inescapable, always moving forward. The singularity is not a place you can avoid, it is a moment in your future, as inevitable as tomorrow. Our intuition fails in such extreme environments, but the mathematics is clear. Time and space blend in ways that defy ordinary experience. Black holes are not just cosmic endpoints. Sometimes they tear apart entire stars before swallowing them. When a star wanders too close to a supermassive black hole, the difference in gravity across the star's diameter becomes so great that it's ripped apart in a process called a tidal disruption event. The star is stretched and shredded, forming a stream of debris. Some of this material falls into the black hole, creating a brilliant flare that can outshine the entire galaxy for weeks or months. The rest is flung outward, escaping into space. Astronomers have observed dozens of these events, using them to study the physics of extreme gravity and the feeding habits of black holes. But black holes also send out signals that are not light at all. When two black holes spiral together and merge, they create ripples in spacetime, gravitational waves. These waves travel across the universe, stretching and squeezing space as they pass. Detecting them requires instruments of incredible sensitivity, like the Laser Interferometer Gravitational Wave Observatory. In 2015, LIGO made history by detecting gravitational waves from a black hole merger, confirming a prediction Einstein made a century earlier. Since then, dozens of mergers have been observed, each one a new window into the hidden population of black holes in the universe. Gravitational waves carry information about the masses, spins, and orbits of the merging black holes. Some of the detected mergers involve black holes in the so-called mass gap, challenging our understanding of how these objects form. Others hint at hierarchical mergers, where black holes created by earlier collisions merge again, building up mass over time. Each detection pushes the boundaries of what we know about the life cycles of black holes. Yet, even black holes are not truly eternal. In 1974, Stephen Hawking showed that black holes can slowly lose mass by emitting what is now called Hawking radiation. This process is incredibly slow for stellar and supermassive black holes, far longer than the current age of the universe, but it means that, given enough time, even the mightiest black holes will eventually evaporate and disappear. The final moments of a black hole's life remain mysterious, as our current theories break down at the smallest scales. Hawking radiation also raises deep questions about the nature of information. When something falls into a black hole, is the information about its structure lost forever? Quantum mechanics says information must be preserved, but Hawking's calculations suggested otherwise. This information paradox has driven decades of research, with some physicists proposing that information is somehow encoded on the event horizon, while others suggest it escapes in subtle correlations within the Hawking radiation. The answer remains one of the greatest mysteries in physics. Black holes have also inspired speculation about even stranger objects. Theoretical solutions to Einstein's equations allow for the existence of white holes, the time-reversed counterparts of black holes, from which nothing can enter and everything can only escape. While white holes are mathematically possible, there is no evidence they exist in our universe. Some theories connect them to the Big Bang, or to hypothetical wormholes, tunnels through spacetime that could, in principle, connect distant regions or even different universes. These ideas remain in the realm of theory and imagination, but they highlight how black holes push the boundaries of what we think is possible. In the end, black holes are not just cosmic oddities. They are laboratories for the most extreme physics, places where our understanding of space, time, matter, and energy is tested to its limits. They shape galaxies, power the brightest objects in the universe, and challenge our deepest assumptions about reality. As we continue to observe, measure, and imagine, black holes will remain at the frontier of science, a reminder that the universe is far stranger and more wondrous than we ever dreamed.